we've covered the basics of the refrigeration cycle. Of course, remember that the refrigeration cycle applies both to refrigerators and air conditioners, as well as heat pumps. And I think we've done a pretty good job of covering each of the four components and how would you analyze those separately, put them all together. But as I was reviewing what we have, I thought I need to add a few more little details to perhaps give a little insight into some actual situations that apply to actual operating uh, air conditioners, refrigerators, and heat pumps. And so this video is associated with some follow-up ideas that I'd like to pass along to you regarding actual cycle considerations. And in a couple of cases, it came to me that there were some really key points that a couple of my thermodynamics professors made that I didn't cover very well in the previous sections. So I want to maybe finish up with some little follow-up notes. Let's refresh our memory on what we have regarding the basic four components of the vapor compression refrigeration cycle. We start with the compressor. And what does that do? Well, of course, that's going to increase the pressure of the refrigerant, say from a saturated or slightly superheated vapor up into the superheated vapor phase where and it's hot, okay? And we condense that refrigerant down. It's still going to be hot at constant pressure, but we're going to condense it down to about a saturated liquid. That's the condenser component. The pressure is going to drop from 3 to 4 through an expansion valve, in other words, a restriction in the line. And we showed that, well, in the absence of kinetic energy change, that's going to be a constant enthalpy process. And with the pressure dropping, and you're going to be underneath the vapor dome, that's what makes that refrigerant really, really cold at state 4. Saturated mixture coming into the evaporator. So we're absorbing heat into the evaporator from a cold space, and it's going to stay cold, and that's what's going to enable us to go back into the compressor and repeat the cycle over and over again continuously. So I think you've got that part, of course. I tried my best to cover basically the ideal refrigeration cycle. Let's refresh our memory on what is the official definition of the ideal vapor compression refrigeration cycle. Well, the compressor, we're going to model the compressor always as adiabatic. But for the ideal cycle, we're going to also say the compressor is reversible. So reversible and adiabatic compressor means we have an isentropic compressor. Now, in the ideal cycle, recognize that I said in most of my work, most of my practical work, I considered the inlet to the compressor to be a saturated vapor. That's part of the definition of the ideal vapor compression refrigeration cycle. It made life easy, didn't it? Because if we know P1, we simply go to the property tables and look up H sub G and S sub G at the pressure P1. So that made life easy on us. Another part of the ideal vapor compression refrigeration cycle was the fact that what comes out of the condenser is a saturated liquid. And that made life easy on us as well, didn't it? It became very easy since if we know P2, which equals P3, we simply go to our refrigerant property tables and look up H sub F at the known pressure P3, it made life easy. I'd like to cover some very subtle points about what about a real life uh, vapor compression refrigeration cycle, whether it's operating as a heat pump or an air conditioner or a refrigerator. And I've just clipped this right out of the textbook. I think it's a very good visualization of what becomes really slightly different for real, honest to goodness refrigeration cycles. So let's start. Well, the compressor. I think I covered it pretty well that in the real world, we know that a compressor is not purely isentropic. It's not purely reversible and adiabatic. So typically, we have a pretty good feel. We can estimate what is the compressor efficiency. And remember, we study the compressor slightly different by recognizing that the compressor is adiabatic but irreversible. So this irreversible adiabatic compressor is one of the primary features of a real world cycle. Now here's another one, is that what goes in sometimes to the compressor inlet would be considered slightly superheated vapor. In other words, the heat that's going into the refrigerant in the evaporator is enough energy to make state one go a little hotter than saturated vapor. And so on this sketch, it does a nice job in communicating. Notice how it's not greatly superheated. I'm calling it slightly superheated. And so in your analysis, when you're analyzing the cycle, what would you do differently? What would you do differently? Well, it would be very slight. You'd go to the superheated tables. You need two independent properties. Since it's not saturated vapor, you need to know the pressure, P1, and you need to know the temperature, T1. So you'd have to have some idea of about how much superheat in degrees C or degrees F is going into heating the refrigerant up above, slightly above the temperature of saturation at P4 equals P1. So that's a second, very subtle part of analyzing a real refrigeration cycle. And the third one, it's really pretty easy. The third one is recognizing that in the condenser component, a lot of times we reject enough heat from the refrigerant to get that temperature slightly below the saturation temperature at P2. So we're still going at constant pressure, but we're taking out enough heat transfer energy in the condenser to slightly subcool it. Well, what does that mean in terms of our work? Well, we know what the pressure is, but notice here we're in the compressed liquid phase of the refrigerant. Now, what do we remember about that? We remember that, well, in the compressed liquid phase, we can look up the enthalpy H. It's a strong function of temperature only. So we don't have to go to separate tables. We would simply go to our saturation table and we would look up H sub F at T3. So all we need to know for a real cycle is about how much subcooling is going on from the saturation temperature of the refrigerant down to T3. And so we'd simply look up H sub F at T3. And amazingly, that kind of covers the three subtle points about analyzing a what we'd call real refrigeration cycle compared to the ideal refrigeration cycle. This is kind of an important point to make that I did not make very clearly in my previous videos. And that has to do with the idea of heat transfer. And do you remember, wow, weeks ago, early on in the class, I think probably chapter 2, where we were talking about what is heat transfer? Well, heat transfer occurs as due to a temperature difference between two interacting systems, thermally connected systems. And remember, on its own, heat only flows from hot to cold. Okay, it takes work to get heat to flow from cold to hot. Well, let's talk about the situation about the condenser. Okay, in the condenser, we've got to transfer heat from the refrigerant into the surroundings. And so this graphically shows that the only way we can transfer heat from the refrigerant into the surroundings is for the surroundings temperature TH to be a little lower than the refrigerant temperature. And so do you see that that TH has got to be somewhat below T3. And so you can see that up here at the outlet, at the inlet of the condenser, compressor outlet, you've got a lot of irreversible heat transfer going on. Look at that, delta T is pretty high here. As you get into the saturation zone, the irreversibility is less, but there is still irreversibility because we're transferring heat across a finite delta T. And so these red lines here give you a visibility of what that finite delta T is all about. So I wanted to depict that and share that with you, that we've got something irreversible going on between the refrigerant and the surroundings. Now, it's the same idea, but not quite as dramatic on the low temperature side. We've got to transfer the evaporator section, process 4 to 1. The only way we can transfer heat from the cold space, let's say the freezer part of your refrigerator, we've got to transfer heat from the cold space into the evaporator. So that means the evaporator temperature, the refrigerant in the evaporator has got to be colder than your freezer. And so I've depicted that here with these red arrows. So notice the delta T, we've got heat transfer flowing from, it's still cold, but heat is flowing from a higher temperature to a lower temperature. And that also represents visually irreversible heat transfer. So notice here, I've got heat transfer from the cold space into the refrigerant. Dr. O'Brien is the individual. He was a department head in mechanical engineering. And when I had him as a thermodynamics professor, he made this point extremely well. And I was able to absorb that. And that really helped me understand another reason why our refrigeration cycles, our real world refrigeration cycles don't have nearly the coefficient of performance that you get from a theoretical Carnot cycle. And so I want to repeat that in words. And so rather than confounding you with all these red arrows, I've tried to write out the conclusion that Dr. O'Brien made so well. It says here, the condenser refrigerant temperature has got to be hotter than the surroundings. That's the only way you can transfer heat from the refrigerant in the condenser into the surroundings. Similarly, the evaporator refrigerant temperature has got to be colder than the cold space. Okay, and so I've depicted that as well. And that's really important from the heat pump standpoint. And so think about now, change your thinking around a heat pump. What are we trying to do with a heat pump? We're trying to heat the inside of our house. That would be the condenser part. And we're trying to absorb heat from the cold outside. And for a heat pump, that's exactly what we're doing here. And so on cold winter days, you've got to recognize that the refrigerant outside in a heat pump is going to be even colder than the cold outside. And I got to tell you, that blows my mind. But it is important. That's an important fact about thermodynamics and these refrigeration cycles. Another one of my thermodynamics professors, Dr. Fury, a senior professor in mechanical engineering, he did a great job of looking at the maximum possible coefficients of performance for both a refrigerator and heat pump. And I recall so vividly him doing that, but also he wanted to look at the numerics of how the values turned out. Let's remind ourselves, how would you calculate the maximum possible coefficient of performance for a refrigerator? And how would you calculate the maximum possible coefficient of performance for a heat pump? I hope that in your minds it pops in your head that the maximum possible coefficient of performance for a refrigerator or air conditioner corresponds to the Carnot cycle, And remember that, well, let's see, energy sought over the energy that costs. We said, okay, the energy sought is QL, and the energy that costs, well, that's the work it takes to drive the cycle. That was QH minus QL. And we remember that for the Carnot cycle, temperatures and heat transfers are proportional. So we got TL divided by TH minus TL. And we plop that down and we kind of use that as a formula. We didn't think much more about it. Let's look at the numerics of this. What's an important part of calculating coefficient of performance for a Carnot cycle? Your temperatures must be in absolute temperature, don't they? And so do you see that TL, or for a heat pump, TH, do you see that the numerator of these two expressions is going to be a pretty big number, isn't it? It's going to be at least 273 degrees K plus. Okay. How about the denominator, TH minus TL? TH minus TL. Numerically, what's that going to be? Gosh, let's say for a refrigerator, TH, what's going to be? That's going to be about 25 degrees C, isn't it? That's room temperature. How about TL? That's going to be about 0 degrees C. Okay. Of course, if we subtract one from the other, we get about 25 degrees, don't we? So we've got a big number divided by a small number. And even if we do that same sort of logic with a heat pump, looking at the outside temperature, well, that might be 0 degrees C. And the inside temperature, well, that would be maybe 25 degrees C. You're trying to heat your home up to about 25 degrees C. You see the same result. Numerically, you've got a big number up here divided by 25. And so do you see that the maximum possible coefficient of performance for the Carnot cycle, for these cycles, it's going to be a big number. And when you run through the calculations for either an ideal vapor compression refrigeration cycle or an actual one, those coefficients of performance are going to be much, much less than the Carnot cycle. And I find that to be an extremely interesting comparison between maximum possible and observed coefficient of performance for either the ideal or the actual vapor compression refrigeration cycle. Another thing that has blown my mind, and it's taken me a long time to understand it, is when we build a house and we choose to heat our house with a heat pump. We buy one unit, don't we? We just buy one air conditioning / heat pump unit. We don't buy a heating unit for the winter and a cooling unit for the summer. It's just one system. And so those systems work both on the vapor compression refrigeration cycle in both seasons. However, they're doing two different functions, aren't they? In the winter, that system is heating your house. In the summer, that system is cooling your house. That kind of blew my mind. How the heck does that work? Well, I want to see if I can chase you to an 8.5-minute video that the This Old House channel in YouTube provides. If you go to, and if you can find the This Old House channel on YouTube and you use a search and you use the search term heat pump, this video is going to pop right up. And you can watch this 8.5-minute video, and it's going to be 8.5 minutes very well spent for you. It certainly was for me, because Kevin and Richard, they do a great job of explaining the basics of the refrigeration cycle. That takes about 4.5 minutes. It's a great review. But then Richard goes on to explain something called a reversing valve. Taking a screenshot of that. And he explains how this reversing valve, when you switch from heat to cool and back and forth up on your thermostat in your home, that's what causes this reversing valve to move. And physically, what it does down in your basement or in your utility closet, is it physically makes the refrigerant go in an opposite direction. And so it turns the condenser into the evaporator, and it turns the evaporator into a condenser, depending on what season you're in. And so it is a reminder that you don't switch from heat to cool several times per day. You're going to select it and you need to leave it. You need to set it and forget it. But these guys just do a great job of explaining in a matter of minutes how the heat pump is transformed into an air conditioner for residential and commercial applications. It's incredible. They do a great job in a very short period of time. Highly recommend it. Another thing that Richard does, sort of at the end of the video, is that he does a great job of explaining a rather new model of heat pump slash air conditioning units, and it's called an inverter style heat pump air conditioner. And when you look outside of houses, instead of seeing the traditional boxy condenser, evaporator, compressor unit out there, you see a much more compact unit that looks like this. And he does a great job of explaining how probably around 2000, right around 2000, because of the advent of very affordable microprocessors, he explains how an inverter style compressor, this is a scroll compressor that can operate at variable speeds. And by enabling the compressor to operate at variable speeds, it helps to fine tune the mass flow rate of refrigerant to get that delta T, the delta T closer from the refrigerant to the cold or hot space temperature. And that improves the coefficient of performance of the heat pump or air conditioning system. He does a great job of explaining this in about a minute and a half. So I admire his ability to encapsulate information and provide it so concisely. So highly recommend you watch this 8.5 minute video to better understand a heat pump slash air conditioning system that we see in our everyday lives. So what's the basic recap of the entirety of Chapter 10? On its own, heat only flows from hot to cold. I tried to make that point in this last video. However, you can make heat flow from cold to hot. Air conditioners, refrigerators, heat pumps. In order to do that, you must invest work or power to drive a compressor to accomplish that objective. And so the vapor compression refrigeration cycle is a wonderful invention, and it has helped transform our everyday lives and make us much more comfortable in our living. The condenser refrigerant temperature must be hotter than the surroundings. That's a big conclusion to recognize. So in the real world, your refrigerant temperature in the condenser has got to be hotter than the surroundings. Similarly, in the evaporator, the refrigerant temperature has got to be colder than whatever cold space you're working with. If it's a freezer, the refrigerant's got to be colder than the freezer. Okay? If it's an air conditioner, the refrigerant temperature has got to be colder than the air you're trying to cool in your house. Well, I hope that helps. So those are some of the subtle points of going from an ideal vapor compression refrigeration cycle to a real vapor compression refrigeration cycle. And I hope that you saw that the changes are subtle. So don't let that scare you away. Don't let anyone scare you away from using an ideal cycle of any type to analyze compared to a real cycle. We engineers can start with ideal cycles analysis, and then with pretty slight changes, quickly get and analyze a real honest to goodness commercial cycle. Hope that helps, and hope to see you again in some of the other videos.